Welcome to a deep dive, everybody. We're really diving into the world where linear algebra just kind of fuels machine learning.
Uh-huh.
You've all brought, hopefully, excerpts from Mathematics for Machine Learning by Dyson-Roth, Faisal, and Ong.
Mm.
It's a book that's become pretty much essential reading in the field. So we're
Yeah.
going to try to extract, I guess, the essence of what you really need to know for this.
Yes, sounds good.
So imagine, picture this. You are diving headfirst into machine learning, right? And you know you need a good grasp, a solid grasp of linear algebra. But you don't necessarily want to go through all of the abstract theory that can sometimes make it hard to,
Yeah.
make your head spin a little bit. This book is really kind of like having that backstage pass because it's written for practitioners, for people like you, not just for mathematicians. It helps you understand not just like the what, but the why behind the tools you're going to be using every single day.
Yeah, and it's true. I mean, this book has really become just something anyone who's serious about machine learning ends up reading at some point.
Right, exactly.
So while it covers a lot, I think we can zero in on what's really going to be most important.
For sure. Think of it like we've created a cheat sheet for you, okay?
Yeah.
With all the most important equations for the book. But we've also added, insider commentary a little bit, what are those called? Like the director's cut DVD extras.
Right, exactly.
Where they tell you what they were thinking and why they made the choices
So
they
behind
made.
the scenes.
Behind the scenes, yeah, exactly. Not that we're comparing ourselves to movie directors or anything like that. But
Yeah.
So yeah, it's not meant to be a replacement for really digging into the book yourself, but it is here to give you a little bit of a head start. Okay.
Sure. Yeah.
So to get us going, let's just break down some of those core linear algebra concepts.
Mhm.
But we're going to keep it super grounded in the real world of data. Okay?
Okay.
All right. We'll start with vectors.
Yeah.
You might be picturing, those little arrows from
Yeah.
physics class. But when we talk about vectors in machine learning, try to think of them more as your data points.
Yeah.
Okay?
Makes sense.
Each feature that you have in your data essentially becomes like a dimension in this vector space. The book actually gives a very simple example. Let's just say you have a 3D vector, right? And this vector has the coordinates 1, 2, 3. Pretty straightforward, right?
Yeah.
Now imagine that this simple vector actually represents a data point with 3 features. So it could be, for example, the height, the weight, and the age of a patient, let's say.
Right, exactly.
Okay, so that's vectors. Let's move on to matrices.
Okay.
Now, I know when you first look at a matrix, it does kind of resemble a data table, right?
Right.
And, in a way, it is. But here's the cool part. Matrices are not just about storing data. They're like the movers and shakers of this whole world. They're what actually transform your data.
Yeah.
One aha moment from the book that really stuck with me was when they said that matrices aren't just these static spreadsheets. They're like verbs.
Oh, interesting.
Right. They act on your data, they shift it, they change it in all these fascinating ways.
Yeah, and the book does a really good job actually of explaining visually how these transformations actually work. Like
Right.
when they're talking about determinants, for instance,
Yeah.
they explain this idea of the signed volume of a matrix,
Right.
And that might sound a little bit abstract at first, but if you think about it, imagine you have some kind of shape, right? And then you apply a matrix to it.
Okay.
The determinant is telling you essentially how much that shape has been squashed or stretched.
Oh, I see.
Right. So if the determinant is 0,
Mm-hmm.
that means you've essentially flattened your shape completely, right? You've kind of lost information in the process.
Lost a dimension or something.
Right, exactly. And that's why a determinant of 0 means a matrix is non-invertible.
Interesting.
You can't reverse that squashing that happened, basically.
Yeah. I'm starting to see how all this connects. So we've got these vectors representing our data points and these matrices, which can act on them like these powerful tools.
Hmm.
But how do we actually use all of this stuff in machine learning,
Right.
What's the practical application?
Yeah, good question.
So let's talk about solving linear equations for a second,
Yep.
okay?
Yep.
I know it sounds like we're going back to high school math class again, but trust me, it's actually way cooler than it sounds, I promise.
Yeah, I hope so.
It's less about the actual calculations themselves and more about the big idea.
Yeah.
Okay? So in the context of machine learning, solving a linear equation, it's kind of like trying to find a secret recipe, if you will. It's like looking for that perfect combination of features that will give you the result that you're hoping for from your machine learning model.
Ah, okay.
And this is where the book, I think, gets really, really practical and helpful,
Yeah.
because it really stresses that you need to know when solutions even exist.
Oh, interesting.
Right. Which can be incredibly useful when you get down the road and you're trying to debug those machine learning models.
Right. Yeah, yeah.
Because sometimes, let's be honest, there just is no magical combination of features that's going to get you to your goal.
Mm.
Knowing that upfront can save you a lot of headaches and a lot of wasted time.
Absolutely, yeah.
Right.
Yeah.
And that's something I really appreciated about the book.
Yeah, it's a really good point. And actually, what's fascinating is how this idea of finding solutions or not finding solutions, it kind of links to some of the even more advanced techniques in the book.
Yeah, like what?
Like, for example, eigenvectors.
Okay.
Now, these might seem kind of like a mathematical curiosity at first glance, but what they really show us is how the data is stretched in very specific directions by a given matrix, right?
Okay, yeah.
And that concept, that stretching in specific directions, it's actually the foundation for techniques like principal component analysis.
Right.
PCA, exactly, which you've probably heard of. It's incredibly useful for a lot of different things, like, for example, compressing images. So they'll take up less space, but they still look good,
Right, right.
Or for analyzing connections in a social network, let's say, to see, like, who the main influencers are. The book even talks about how this applies to biological neural networks.
That's incredible, yeah.
It's really fascinating stuff.
So these eigenvectors are like, they're not just theoretical. They have real-world
It's
application.
fundamental, yeah.
They're the basis for a lot of really powerful tools.
For sure.
Before we jump into those, though, what stands out to you about how matrices can represent these transformations? Have you seen that in your own work at all?
It really is all about perspective, isn't it? Like, I've always been fascinated by how, in machine learning especially, we're dealing with these massive, huge data sets, right? And matrices give us this way to just like move that data around and manipulate it in really efficient ways. It's like having, I don't know, a set of levers that can just shift this whole landscape.
That's a great analogy. It's like those massive earth-moving machines you see at construction sites where just one person can move mountains of dirt.
Right, exactly. It's that kind of power.
So we've got these powerful matrix transformations, but the book also goes into some, even more complex tools like singular value decomposition, or SVD, as the cool kids call it.
Right, right.
I'll be honest, that one sounds a little intimidating to me.
Yeah, it could sound kind of scary at first, right?
Yeah, a little bit.
But if you think about it like this, imagine you've got this really delicious cake, okay? And you want to know, like, what is it that makes this cake so good?
Okay, yeah.
SVD is kind of like if you could break that cake down into its core ingredients. Like, okay, we've got flour, we've got sugar, we've got eggs, and you can see the exact proportions of each ingredient that make that cake work.
Okay.
That's kind of what SVD is doing with matrices,
So it's like reverse engineering a cake, but instead of getting a recipe, we're getting at the core components of a matrix.
Exactly. Yeah, you got it.
But how does that apply to machine learning in practice? Like, what's a concrete example?
Okay, so let's say you're building a recommendation system, right? Like, think Netflix or Amazon.
Okay.
You could have this giant matrix, right, where each row is a different movie, each column is a user, and then the entries in the matrix are the user ratings for each movie.
Okay.
SVD can take this massive matrix and break it down into smaller, more manageable pieces, and these pieces can then reveal these hidden patterns in the data, like which genres tend to be enjoyed by similar groups of users.
Oh, interesting. So, like, if I love sci-fi movies and I give high ratings to Star Wars and Arrival,
Right.
SVD might find, like, a whole group of other users out there with similar taste.
Exactly.
And the recommendation system could then say, hey, these other users also really like this other movie that you haven't seen yet.
Exactly. That's exactly it. SVD helps us find those connections and make those recommendations even better. And it's not just recommendations, it's also used in image compression, noise reduction, all sorts of cool applications.
Wow. So it's really versatile.
It's super versatile. And you know what's really interesting? This actually ties back to what we were talking about earlier with eigenvectors, believe it or not.
Oh, you're right.
Yeah.
Because eigenvectors show us how data is stretched by a matrix. And SVD is all about, like, breaking down that matrix. So they really are two sides of the same coin.
Exactly. And that brings us to another fascinating area, the pseudo-inverse. Now, remember how we were talking about matrices being like verbs,
Yeah,
right?
they're acting on the data.
Acting on the data, exactly. Well, sometimes you need to reverse that action. It's like finding the undo button, so to speak. But what if that matrix, what if it squashed the data down to zero, right? Like we were talking about with determinants.
Right.
That's where the pseudo-inverse swoops in.
So it's like, Okay. It's like when you accidentally hit save on a document, right?
Yeah.
And you're like, no,
Yeah.
I didn't want to save that version. And you're trying to like frantically find a way to recover what you had before. So the pseudo-inverse is like that undo button for matrices, even in those cases where a true inverse doesn't exist.
Yeah, that's a great way to put it. Like it's finding the closest possible undo in those situations where a perfect reversal just isn't possible. And this has real world implications too. Remember we were talking about GPS earlier?
Yeah.
Your phone's GPS, it uses the pseudo inverse to figure out your location from just those few satellite signals. Even though technically there's not enough information there to get a perfect solution,
Right.
it uses the pseudo inverse.
Wow, that's fascinating. So it helps us deal with those real-world situations where we don't have all the information we ideally want.
Uh-huh.
And speaking of dealing with those less than ideal situations, the book also mentions something called the Koleski decomposition,
Right.
which kind of sounds like a medical procedure.
It does sound a little intimidating, doesn't it?
It does, yeah.
But think of it this way, okay? Remember we were talking about finding the square root of a matrix?
Yeah.
Cholesky decomposition is kind of like that, but it only works on these very special types of matrices that are symmetrical. Like imagine something that's a perfect mirror image of itself, you know?
Okay.
That kind of matrix.
Okay.
It's a way to break down these special matrices into simpler components, which then makes certain calculations way faster.
So it's kind of like having a shortcut for a certain situation.
Exactly, yeah. That's a good way to think about it.
But when would we actually use this Koleski decomposition in machine learning, practically speaking?
It's super useful for tasks like generating random data that follows a specific pattern. Let's say you're training a machine learning model, right?
Okay.
And you need more data. Like you just need more data that's similar to what you already have. Koleski decomposition can help you generate this kind of synthetic data very quickly, which is super valuable in situations where real data is either hard to come by or maybe it's really expensive to collect.
That makes a lot of sense. So it's like having a magic wand almost that can just like conjure up more data when you need it. You know, it's really amazing to me how all of these different concepts we talk about, vectors, matrices, eigenvectors, SVD, pseudo-inverse, they all kind of fit together. Like they're all pieces of this bigger puzzle.
Yeah, absolutely.
But I'm curious, how do these more advanced concepts, how do they all play into the bigger picture of machine learning? Like at what point in the workflow, I guess, do they become relevant?
You're right. It's all interconnected. And to answer your question, these concepts are really the backbone of so many different machine learning algorithms. Take convex optimization, for instance.
Okay.
It might sound kind of like a mouthful,
It does, a little bit.
but it's really about finding the absolute best solution to a problem, not just something that's like good enough.
Okay.
We want the best of the best.
So instead of just kind of like stumbling around in the dark, hoping we're going in the right direction, convex optimization gives us a more like clear path to that optimal solution.
Exactly. It's like you're
Yeah.
climbing a mountain. And convex optimization is like having that trail map and you've got your compass. You know if you follow the path, you're going to reach the summit.
Okay.
And the cool thing is, so many machine learning problems can actually be framed as these convex optimization problems,
Oh, wow.
which means we can use these really powerful tools to find like the absolute best solution for our models.
That's amazing. So it's like, it's almost like having a guarantee in a world that's otherwise like full of uncertainty.
Exactly. Yeah.
But even with all of these incredible tools, there are still limitations, right?
You're absolutely right. There's this idea in machine learning. It's called the no free lunch theorem,
Okay.
which basically says like there's no one best machine learning algorithm that will just magically work perfectly for every single situation.
That makes sense, yeah. It's like having a toolbox full of different tools, right? You wouldn't use a hammer to try to tighten a screw.
Exactly. You got to choose the right tool for the job.
Right, exactly. You need the right tool for the job.
Yeah.
And that actually reminds me of this one time when I was trying to fix a leaky faucet.
We've all been there.
Oh, man, it was a disaster. But, you know, it's a good analogy because in machine learning, we have to really think critically about the problem we're trying to solve. We have to look at the data we have. And we need to think about the strengths and the weaknesses of all these different algorithms that are available to us. There's no one magic bullet.
Absolutely not. And that's what makes it so interesting, right?
Right, exactly. It keeps us on our toes. So it's all about being adaptable, understanding those tools that we've got in our toolbox, and then just making these informed decisions based on the situation.
Exactly. Yeah.
And honestly, that's what's made this deep dive so valuable for me, personally. Hmm. We've gone from those really fundamental concepts like vectors and matrices all the way to these much more advanced tools, SVD, pseudo-inverse, convex optimization. I feel like I'm actually starting to see how it all fits together.
Exactly, yeah. It's like we've been building this machine piece by piece,
Yeah,
and now we can kind of see how all the gears and levers actually work together to create something really powerful.
yeah. No, that's a great analogy. I really like that. So as we kind of wrap up our exploration of linear algebra and machine learning here, what's like the one most important thing you would want our listeners to take away from all of this?
I think it's important to remember that linear algebra, it's not just about memorizing a bunch of equations and formulas. It's really more like a language, a way of thinking about data, a way of interacting with data that's absolutely fundamental to how machine learning works. So by grasping these concepts, you're not just, memorizing stuff, you're developing this deeper intuition for how data works and how to use it.
It's like learning the secret code that makes everything else make sense.
Exactly. It's incredibly empowering.
Absolutely. So to leave our listeners with one final thought-provoking question here. The book spends a lot of time talking about using matrices to represent these linear transformations, right?
Right.
But what other kinds of transformations could be useful in this world of machine learning?
Hmm.
And how could we even begin to represent those? That's something to kind of ponder as you continue on your learning journey here.
Absolutely, yeah. And remember, everyone, this deep dive was really just a little taste of this incredible world. There's so much more out there to explore.
Right, yeah.
Mathematics for machine learning, it's a fantastic resource for those of you who want to go even deeper, and I know you will.
Yes, definitely check it out.
Keep exploring, keep asking questions, and keep that curiosity alive.
And that is a wrap on our deep dive into the fascinating world where linear algebra and machine learning collide. We hope you found it enlightening, inspiring, and maybe even a little bit mind-blowing. We had a blast, and we can't wait to join you on your next learning adventure. Until then, keep those brains buzzing.